This video is brought to you by mywayteaching.com.
So in this figure you can see a uniformly polarized dielectric amounts to induced surface charge density but no volume charge density. The common question is, how does the polarized dielectric modify the external field inside it? So now let us consider a rectangular dielectric slab placed in a uniform electric field E0 parallel to two of its faces, as you can see in this particular figure. This field causes a uniform polarization P of the dielectric. Okay. Thus, every volume element delta V of the slab has a dipole moment which is given by P into delta V in the direction of field. And the volume element is macroscopically small but contains a very large number of molecular dipoles. So, anywhere inside the dielectric, the volume element delta V has no net charge. This is because the positive charge of one dipole is close to the negative charge of the adjacent dipole, isn't it? However, at the surfaces of the dielectric normal to the electric field, there is evidently a net charge density at the surfaces. The positive ends of the dipoles remain unneutralized at the right surface, this one, and at the left, negative ends at the left surface. The unbalanced charges are the induced charges due to external field. So thus, the polarized dielectric is equivalent to two charged surfaces with induced surface charge densities, that is sigma p and minus and plus sigma p. Thus, the total field in the dielectric is thereby reduced from the case when no dielectric is present. We should note that the surface charge density plus or minus sigma p arises from bound in the dielectric. Now we are going to study the most important part, that is capacitors and capacitance. See, a capacitor is a system of two conductors separated by an insulator. The conductors have charges say Q1 and Q2 and potentials V1 and V2. So we can say capacitors in general as two conductors separated by an insulator. Okay. The two conductors have charges usually plus Q and minus Q, and the potential difference V, that is given by V1 minus V2. So we shall consider only this kind of charge configuration of the capacitor. The conductors may be so charged by connecting them to the two terminals of a battery. Q is called charge of the capacitor. Through this, in fact, is the charge on one of the conductors. The total charge of the capacitor is 0. Okay. And the electric field in the region between the conductors is proportional to the charge Q. Okay. So this is conductor 1, conductor 2 separated by an insulator. So we can call it as capacitor. See, if the charge on the capacitor is say doubled, the electric field will also be doubled at a V point. Now, potential difference V is the work done per unit positive charge in taking a small test charge from conductor 2 to conductor 1 against the field. So, V is also proportional to Q. So, we can write C is equal to Q by V. This constant C, we call it as capacitance of a capacitor. and this C is independent of Q or V. The capacitance, it depends only on the geometrical configuration, which means it depends only on the shape, size and separation of the system of two conductors. Okay, and the SI unit of this capacitance is given by 1 farad. The SI unit is farad. And this 1 farad is equal to 1 coulomb per volt. A capacitor with fixed capacitance is symbolically, we'll represent it like this. A capacitance with variable capacitance, it is represented like this. Okay. And this equation, we call it as equation A. It shows that for large capacitance C, V is small for a given Q. This means a capacitor with large capacitance cannot hold large amount of charge Q at a relatively small V, isn't it? So this is of practical importance. High potential difference implies strong electric field around the conductors. A strong electric field can ionize the surrounding air and accelerate the charges so produced to the oppositely charged plates, thereby neutralizing the charge on the capacitor plates. In other words, we can say the charge of the capacitor leaks away due to reduction in insulating power of the intervening medium. If the electric field is so strong, then it ionizes the charges in the insulator and the electric charges flows, isn't it? So the maximum electric field that a dielectric medium can withstand without breakdown is called as dielectric strength. Okay. Without breakdown, how much it can withstand, that is called as dielectric strength. It is for air, it is about dielectric strength for air 3 into 10 raised to 6 volt per meter. For a separation between conductors of order 1 centimeter or so, this field corresponds to a potential difference of 3 into 10 raised to 4 volt between the conductors. Okay. Thus, for a capacitor to store a large amount of charge without leaking, its capacitance should be high enough so that potential difference and hence the electric field do not exceed the breakdown limits. So there is a limit to the amount of charge that can be stored on a given capacitor without significant leaking. Okay. The most common units are, we will use submultiples like microfarad, nanofarad. So 1 microfarad is given by 10 raised to minus 6 farad. 1 nanofarad is given by 10 raised to minus 9 farad. And 1 picofarad is given by 10 raised to minus 12 farad. So besides its use in storing charge, a capacitor is a key element of most AC circuits. Okay. Now let us study one of the important type of capacitor, that is parallel plate capacitor. What is this parallel plate capacitor? See, a parallel plate capacitor, it consists of two large plates parallel conducting plates separated by a small distance. You can see in this figure two parallel plates separated by a distance. It forms a parallel plate capacitor, isn't it? See, we first take the intervening medium between the plates to be vacuum. The effect of a dielectric medium between the plates is very much important. So let us consider A to be the area of each plate and D the separation between them. You can see A is area, D is the separation. The two plates have charges plus Q and minus Q. Since D is much smaller than the linear dimension of the plates, we can say D square is very much less than A. So we can use the result on electric field by an infinite plane sheet of uniform surface charge density. Plane 1 has surface charge density that is given by this plate 1. Surface charge density Q by A, and this one is minus Q by place 2. Yeah, this is minus Q by A. So the electric field in different regions. Outer region 1, the electric field is given by So at region 1, the electric field is given by sigma by 2 epsilon naught minus sigma by 2 epsilon naught is equal to 0. At outer region 2, the electric field is given by sigma by 2 epsilon naught minus sigma by 2 epsilon naught is 0. In the inner region between plates and 1 and 2, the electric field due to two charged plates is given by sigma by 2 epsilon sigma by epsilon naught, that is given by q epsilon naught, q by epsilon naught into A. Okay, and the direction of electric field is from positive to the negative field. So the electric field is localized between the two plates and it is uniform throughout. For plates with finite area, there will not be true near the outer boundaries of the plates. The field lines bend outward at the edges, an effect called fringing of the field. In that case, sigma will not be strictly uniform on the entire plate. Okay. However, for D square very much less than A, these effects can be ignored in the region sufficiently far from the edges. And the field there is given by this E is equal to Q by epsilon naught A. So now for uniform electric field, potential difference is simply the electric field times the distance between the plates. So that potential difference is given by ED, that is Q D epsilon naught into A. The capacitance C of a parallel plate capacitor is given by C is equal to Q by V, which is equal to epsilon naught A by D, isn't it? Yes. So it depends only on the geometry of the system, shape, size, separation. For typical values like A is equal to 1 meter square, B is equal to 1 mm, we get C is equal to 8.85 into 10 raised to minus 12, 1 and 1 mm 10 raised to minus 3. It is equal to 8.85 into 10 raised to minus 9 farad. Okay. If you consider area A, C D by epsilon naught, if you take C as 1 farad, D 10 raised to minus 2 meter, and we get 10 raised to 9 meters square, which is a plate about 30 kilometer in length and breadth. Okay.